Section 7.1, what is a sampling distribution? The United States Census Bureau selected a random sample of more than 60,000 people with at least a bachelor's degree and found that their mean income in the sample was $78,862. Now, this would be called a sample mean. It's a statistic because it's based on a sample of people. These 60,000 people are representing the whole population of the United States with respect to those with at least a bachelor's degree. They are a point estimate for the entire population of all people. And ideally, we'd be able to go out and talk to every single person and find out this population parameter. What's the average income for all of these people? However, that'd be very hard to do because the population is just so large. So how close is this estimate of $78,862 to the actual mean of all people in the US with at least a bachelor's degree? So as I just mentioned, that value is a statistic. And it's a statistic because it describes this one sample. Every time we take a different sample of 60,000 people, or whatever size sample we're talking about, we're going to get a different average. So this value will change depending on the people that we select. However, there is some true average, some overall average. If we went out and spoke to every single person in the US with a bachelor's degree and found out how much they made, we would be able to find that average. And that would be the population mean, which is the parameter that we're interested in. So we're trying to figure out what is that parameter, the mean of all people in the US with respect to their income, by only talking to a subset, a small group of them. Now, in many cases, parameters are unknowable values. We can never know the actual average income of those in the US with at least a bachelor's degree because it's just not feasible to think that we could go and contact every single person. So instead, we deal with samples, right? Rather than talk to everybody, we'll select a randomly selected group from the whole population and we'll get a statistic that's calculated from that random sample. Now, the first thing that it's important to get clear on is all of this terminology. So remember your S's and P's. Statistics come from samples, and parameters come from populations. We use different symbols to differentiate these values. So rather than saying statistic, we know it's a statistic based on the variable we use. X bar for a mean, P hat for a proportion, SX for standard deviation. If we're dealing with the population, we talk to everybody in our whole population. The mean would be mu. The population proportion would be P instead of P hat. And the standard deviation would be sigma. So let's identify the population, the parameter, the sample, and the statistic in each of these following settings. In part A, we have a Pew Research Center poll, which asked 743 13 to 17-year-olds in the US, do you have access to a smartphone? Of those respondents, 95% said yes. So our sample is the group of 13 to 17-year-olds that we spoke to. There were 743 of them. That's the sample. The statistic is the value that came from that sample. Of those 743, 95% said, yes, I have access to a smartphone. Now that value is representing the population of all 13 to 17-year-olds in the United States, and that 95% is estimating the parameter, which is the true proportion of all these 13 to 17-year-olds in the US that have access to a smartphone. Now let's do one more example where we're not taking a survey of multiple people. Here we have Tom, who's roasting a large turkey breast for a holiday meal, and he wants to be sure it's safe to eat and has a minimum internal temperature of 165 degrees. So he uses a thermometer. He checks this turkey breast at 4 randomly chosen locations to find that the minimum reading is 170 degrees Fahrenheit. So the sample is the readings that we take. And in this case, we're taking thermometer readings from these 4 randomly chosen locations. All of our samples should be done randomly. The statistic is the value that we get from that sample. In this case, the minimum reading from those 4 locations is 170 degrees Fahrenheit. This is representing the population of the internal temperature all across the turkey breast at all locations. And the parameter that we're estimating is the true minimum temperature. So we want to make sure that across this entire turkey breast, everywhere, it's above 165 degrees. This slide is referencing the penny for your thoughts activity, which we did in class. In case you were absent that day or we haven't done it yet, we take a sample of a number of pennies and we record the year of each penny and we record whether or not it was minted after the year 2000. And we find the proportion of pennies that are minted in 2000 or later, and we find the average year that all these pennies were minted. When we make our dot plots, we see approximately symmetric graphs in both of our distributions. So what these graphs are showing is a sampling distribution. Each dot on our graph is representing a sample, and each dot is representing the proportion of pennies in that sample that were minted after 2000, or it's representing the average mint year for our sample of pennies. Okay, so a sampling distribution is changing an original distribution by taking a sample from that distribution and calculating a statistic for it. In this example, we have Mrs. Chauvet, who shows her class a box filled with black and white beads, with the proportion of black beads being 50%. To figure out how many homework problems they'll get, she has a student select a simple random sample of 30 beads, and however many black ones there are is the number of problems they'll get. The sample results in 19 out of 30 being black. Now this value, this statistic, is above 63%, and the students are suspicious. They think that's too high, right? Does this indicate that the actual proportion of black beads in this box is more than 50%? To figure this out, we have a simulation of 100 simple random samples of the same size, n equals 30. In each of these samples, they calculate the number that were black and convert it to a percentage. So every one of these dots represents a sample of 30 beads and the proportion which are black. In part A, it references one dot on the graph that has a p-hat of 0.77. Now, p-hat is indicating that this is a sample. It's asking us to explain what this dot represents. So here's our dot over here. For this particular sample, now remember, every dot in this dot plot is representing 30 beads. So for this particular dot, it's representing a sample size of 30, where 77% of those beads were black. And that's the case for all of the dots in this sample. There are 100 dots in the sample. In part B, it's asking us, would it be unusual to get a sample proportion, a p-hat, of 0.63 or greater? So when we look at this graph, we want to see how likely was that. So 0.63 looks like it's about here, all these graphs, all these dots. And we could add those up and we see 1, 2, 3, 4, 5, 6, 7, 8. There's 9 dots that are at 0.63 or greater. Is that unusual? No, it's not. That's not less than 5%. This will happen fairly likely just by chance when half the beads in our sample are black. And with that information, is there convincing evidence that Mrs. Chauvet lied about the contents of the box and the proportion of all beads that were black? Now, in the actual sample, when they assigned the homework problems, they got 63%. That's not what this graph is. This graph is showing us simulated samples. So we simulated selecting samples from a population where 50% of the beads were black and 50% were white. And we found that 9 of those samples out of 100 had results that were equal or more extreme than the one that they got in the actual sample when homework was assigned. So because this is somewhat likely to occur just by chance, it means that there's not convincing evidence that Mrs. Chauvet lied. This result can happen. It's reasonable to expect to happen just by chance alone. This dot plot here is a sampling distribution. More specifically, it's a partial sampling distribution. Each dot in this graph represents a sample of 30 beads calculated into a proportion of how many were black. In an actual sampling distribution, we wouldn't just take 100 simulated samples. Instead, we would take every possible sample of 30 beads that we could possibly draw from our whole population. That's a true sampling distribution. Since we only did this 100 times, this is a partial sampling distribution or approximation of the actual sampling distribution of the proportion of beads that are black. As long as we have enough trials in our sample, this is a good enough approximation of the full sampling distribution that we can use it to solve problems.